2. Lab 2, Motion of a Falling Object. The purpose of the lab was to quantify motion of an object falling straight down as it is affected by gravity and drag force. To do this, we must drop an object that is lighter than a rock, meaning less dense and lower mass, and compare it to a computational model of that object falling without any drag force. The principles applied to this lab are Newton's second law, taking drag force and weight into consideration when finding F net. In this lab, the system is the ping pong ball and its surroundings are everything acting upon it, such as gravity and air. The mass of the ping pong ball is 2.7 grams and the diameter is 0.04 meters. These are important for calibrating the tracker program and updating my computational model. After recording my video and uploading it to the tracker program, I used a calibration stick to measure the diameter of the ping pong ball and set my axes to be in the center of the ball. In this lab, any change in the x direction did not matter, so I also had to change the plot to be the y position versus time. Here, you can see the movement of the ball beginning at a start time of t equals 0 seconds. As it falls in the negative y direction, a total of 2.353 meters until it hits the ground at t equals 0.735 seconds. For this lab, it was required to construct two computational models, one with only the effects of gravity and one with the effects of gravity and drag. For the model with only gravity, I began with the starter code and updated the mass of the object, the delta t, and made sure the drag constant was 0. I then made sure the code knew to stop running at 0.734 seconds and updated all of the equations to be able to find the net force. Since drag is 0 in this, the net force will just be equal to the weight force of the ball. Then I ran the program and observed the ball moving down in the negative y direction and producing a negatively curved position versus time graph that looks very similar to the one seen in the tracker program. For the model including gravity and drag, I used the same code with the initial changes such as mass and delta t, but through trial and error, I found the b value that gave me the closest y value to the one in the experimental model. I used the same equations to find the F net, but since drag is not 0, it will yield a different result. The last thing I did was to make sure I had arrows showing both gravitational and drag forces on the ball. I ran the program and observed a similar motion of the ball, and now I can compare all three models using Google Sheets. Using Google Sheets, I created a position versus time plot with all three models' data. The blue line represents the experimental data, the red line represents the computational model with gravity and drag, and the yellow is the computational model with only gravity. As you can see, the model with gravity and drag is very close to the experimental data, but the model without drag fell quicker and would have hit the ground sooner than those with drag force. The small discrepancies between the experimental and computational model with drag could be due to outside forces from the surroundings acting on the ball. The question arises if either model will predict a terminal velocity. In this case, the model including drag force does. Eventually, the drag force will act against gravity and thus cause the net force to be 0. Due to Newton's second law, this means that the velocity will no longer increase once it reaches the terminal velocity of negative 6.54 meters per second. The model without drag force would just continue to accelerate and never reach a terminal velocity. If the object would be thrown down instead of just dropped, the terminal velocity would be the same. This is because it is dependent on the mass, surface area, and density of the air it is falling through. Since none of these changed, even with the addition of an initial velocity, the terminal velocity remains the same. Thank you for taking the time to watch my lab.